Some, like the Hawaiian island, Emperor Seamount Chain, which stretches from the Hawaiian Islands to the Aleutian Trench, form overvolcanic hot spots. Others are born near oceanic ridges. If a volcano grows large enough before plate motion carries it away from its magma source, the structure may emerge as a volcanic island. Examples of volcanic islands include Easter Island, Tahiti, Bora Bora, the Galapagos Islands, and the Canary Islands. Geos. Inactive volcanic islands are gradually but inevitably lowered to near sea level by the forces of weathering and erosion. As a moving plate slowly carries volcanic islands away from the elevated oceanic ridge or hot spot over which they formed, they gradually sink and disappear below the water surface. Submerged, flat-topped seamounts that formed in this manner are called geos. The term geo is named after Arnold Guyot, Princeton University's first geology professor. It is pronounced Geo with a hard G, as in give. Oceanic plateaus. The ocean floor contains several massive oceanic plateaus. Resembling the flood basalt provinces found on the continents, oceanic plateaus are thought to form when the bulbous head of a rising mantle plume melts, producing vast outpourings of fluid basaltic lavas. Some oceanic plateaus appear to have formed quickly in geologic terms. Examples include the Ontong Java Plateau, which formed in less than 3 million years, and the Kerguelen Plateau, which formed in 4.5 million years. Explaining coral atolls, Darwin's hypothesis. Coral atolls are ring-shaped structures that extend from slightly above sea level to depths of several thousand meters. What causes atolls to form, and how do they attain such great thicknesses? Corals are tiny animals that generally cluster in large numbers and form colonies when linked. Most corals create a hard external skeleton made of calcium carbonate. Some build large calcium carbonate structures, called reefs, where new colonies grow atop the strong skeletons of previous colonies. Sponges and algae may attach to the reef, enlarging it further. Reef-building corals grow best in waters with an average annual temperature of about 24 C. They cannot survive prolonged exposure to temperatures below 18 C or above 30 C. In addition, reef builders require clear, sunlit water. Consequently, the depth of most active reef growth is limited to no more than about 45 meters. The strict environmental conditions required for coral growth create an interesting paradox. How can corals, which require warm, shallow, sunlit water no deeper than a few dozen meters, create thick structures such as coral atolls that extend to great depths? The naturalist Charles Darwin was one of the first to formulate a hypothesis on the origin of ring-shaped atolls. He did this during a 5-year period, when he sailed aboard the British ship HMS Beagle on its famous global circumnavigation. On this journey, Darwin visited many volcanic islands surrounded by coral reefs. A keen observer, Darwin noticed a progression in coral reef development from a fringing reef along the margins of a volcano to a barrier reef with a volcano in the middle to an atoll, consisting of a continuous or broken ring of coral reefs surrounding a central lagoon. Figure 10.12 Darwin's hypothesis. Darwin's hypothesis asserts that, in addition to being lowered by erosional forces, many volcanic islands gradually sink. Darwin also suggested that corals respond to the gradual change in water depth caused by the subsiding volcano by building the reef complex upward. Atolls may eventually become geos, when the rate of subsidence exceeds the ability of corals to build up the reef, or when the reef-building organisms die out. Figure 10.12 Full alternative text description. The essence of Darwin's hypothesis is that, in addition to being lowered by erosional forces, many volcanic islands gradually sink. Darwin also hypothesized that corals responded to the gradual change in water depth caused by the subsiding volcano by building the reef complex upward. Eventually, the volcano would submerge beneath the sea, and its remnant would be covered by a type of reef we call an atoll. During Darwin's time, however, there was no plausible mechanism to account for how or why so many volcanic islands sink. The plate tectonics theory provides the most current scientific explanation of how volcanic islands become extinct and sink to great depths over long periods of time. Some volcanic islands form over relatively stationary mantle plumes, causing the lithosphere to be warmed and buoyantly uplifted. Over spans of millions of years, these volcanic islands gradually sink as the moving plates carry them away from the region of hotspot volcanism because the lithosphere cools, becomes denser, and sinks. Volcanic islands that form on spreading centers also sink when they move away from these areas of upwelling. The plate tectonics theory provides the most current scientific explanation regarding how volcanic islands become extinct and sink to great depths over long periods of time. Some volcanic islands form over relatively stationary mantle plumes, causing the lithosphere to be buoyantly uplifted. Over spans of millions of years, these volcanic islands gradually sink as the moving plates carry them away from the region of hotspot volcanism. Figure 10.13 Full alternative text description. Figure 10.13 Plate tectonics and coral atolls. Concept checks 10.3. 1. Explain how deep ocean trenches are related to plate boundaries. 2. Why are abyssal plains more extensive on the floor of the Atlantic than on the floor of the Pacific? 3. How does a flat-topped seamount, called a guyot, form? 4. What features on the ocean floor most resemble flood basalt provinces on the continents? 5. Using Darwin's hypothesis, place these coral reefs in order from youngest to oldest: barrier reef, atoll, and fringing reef. 10.4 Anatomy of the oceanic ridge. Sketch and label a cross-sectional view of the Mid-Atlantic Ridge. Explain how a cross-section of the East Pacific Rise would look different. Along well-developed divergent plate boundaries, the seafloor is elevated, forming a broad linear swell called the oceanic ridge, or mid-ocean ridge or rise. Our knowledge of the oceanic ridge system comes from soundings of the ocean floor, core samples from deep-sea drilling, visual inspection using deep-diving submersibles, and first-hand inspection of slices of ocean floor that have been thrust onto dry land during continental collisions. This submersible is 7.6 meters long, weighs 16 tons, has a cruising speed of 1 knot, and can reach depths of 4,000 meters. A pilot and 2 scientific observers are along during a normal 6 to 10 hour dive. Figure 10.14 The Deep Diving Submersible Alvin. The oceanic ridge system winds through all major oceans in a manner similar to the seam on a baseball, and it is the longest topographic feature on Earth, exceeding 70,000 kilometers in length. The crest of the ridge typically stands 2 to 3 kilometers above the adjacent deep ocean basins and marks the plate boundary, where new oceanic crust is created. Figure 10.15 The oceanic ridge system. Figure 10.15 Full alternative text description. Notice in Figure 10.15 that large sections of the oceanic ridge system have been named based on their locations within the various ocean basins. A ridge may run through the middle of an ocean basin, where it is appropriately called a mid-ocean ridge. The Mid-Atlantic Ridge and the Mid-Indian Ridge are examples. By contrast, the East Pacific Rise is not a mid-ocean feature. Rather, as its name implies, it is located in the eastern Pacific, far from the center of the ocean. The term ridge is somewhat misleading because these features are not narrow and steep, as the term implies, but have widths from 1,000 to 4,000 kilometers and the appearance of broad, elongated swells that exhibit varying degrees of ruggedness. Furthermore, the ridge system is broken into segments that range from a few tens of kilometers to hundreds of kilometers in length. Each ridge segment is offset from the adjacent segment by a transform fault. Oceanic ridges are as high as some mountains on the continents, but the similarities end there. Whereas most mountain ranges on land form when the compressional forces associated with continental collisions fold and metamorphose thick sequences of sedimentary rocks, oceanic ridges form where upwelling from the mantle generates new oceanic crust. Oceanic ridges consist of layers and piles of newly formed basaltic rocks that are buoyantly uplifted by the hot mantle rocks from which they formed. Along the axis of some segments of the oceanic ridge system are deep, down-faulted structures called rift valleys because of their striking similarity to the continental rift valleys found in East Africa. Some rift valleys, including those along the rugged mid-Atlantic ridge, are 30 to 50 kilometers wide and have walls that tower 500 to 2,500 meters above the valley floor. This makes them comparable to the deepest and widest part of Arizona's Grand Canyon. The axes of some segments of the oceanic ridge system contain deep down-faulted structures called rift valleys that may exceed 30 to 50 kilometers in width and 500 to 2,500 meters in depth. Smart Figure 10.16 Rift Valleys. Concept Checks 10.4. Watch tutorial, Seafloor Spreading. 1. Briefly describe the oceanic ridge system. 2. Although oceanic ridges can be as tall as some mountains found on the continents, list some ways in which the features are different. 10.5 Oceanic ridges and seafloor. Spreading. Write a statement describing how spreading rates affect ridge topography. The greatest volume of magma is produced along the oceanic ridge system in association with seafloor spreading. As plates diverge, fractures created in the oceanic crust fill with molten rock that gradually wells up from the hot mantle below. This molten material slowly cools and crystallizes, producing new slivers of seafloor. This process repeats in episodic bursts, generating new lithosphere that moves away from the ridge crest in a conveyor belt fashion. Did you know? If you were thinking about buying an island hideaway, the Indian Ocean might be the place to look. Numerous small coral islands, including the Maldives, are scattered about the Indian Ocean. The Maldives include more than 1,000 islands, most of which are uninhabited. Rising sea levels, however, threaten many of these low-lying coral masses. Seafloor spreading. Harry Hess of Princeton University formulated the concept of seafloor spreading in the early 1960s. Later, geologists were able to verify Hess's view that seafloor spreading occurs along the crests of oceanic ridges, where hot mantle rock rises to replace the material that has shifted horizontally. Recall from Chapter 4 that as rock rises, it experiences a decrease in confining pressure that may lead to decompression melting. Partial melting of ultramafic mantle rock produces basaltic magma that has a surprisingly consistent chemical composition. The newly formed melt separates from the mantle rock and rises toward the surface. Along some ridge segments, the melt collects in small, elongated reservoirs located just beneath the ridge crest. Eventually, about 10 to 20% of the melt migrates upward along fissures and erupts as lava flows on the ocean floor, while the remainder crystallizes at depth to form the lower crust. This activity continuously adds new basaltic rock to diverging plate margins, temporarily welding them together. They are then broken as spreading continues. Along some ridges, outpourings of pillow lavas build submerged shield volcanoes as well as elongated lava ridges. At other locations, more voluminous lava flows pave the surface to create a relatively subdued topography. Why are oceanic ridges elevated? The primary reason for the elevated position of the ridge system is that newly created oceanic lithosphere is hot and therefore less dense than cooler rocks of the deep ocean basin. As the newly formed basaltic crust travels away from the ridge crest due to seafloor spreading, it is cooled from above as seawater circulates through the pore spaces and fractures in the rock. Further cooling occurs as this new rock gets farther and farther from the zone of hot mantle upwelling. As a result, the lithosphere gradually cools, contracts, and becomes denser. This thermal contraction accounts for the greater ocean depths that occur away from the ridge. After about 80 million years of cooling and contraction, rock that was once part of an elevated ocean ridge system becomes part of the deep ocean basin. As lithosphere is displaced away from the ridge crest, cooling also causes a gradual increase in lithospheric thickness. This happens because the boundary between the lithosphere and asthenosphere is a thermal boundary. Recall from Chapter 9 that the lithosphere is Earth's cool, stiff outer layer, whereas the asthenosphere is a comparatively hot and weak layer. As material in the uppermost asthenosphere ages, it becomes stiff and rigid. Thus, the upper portion of the asthenosphere is gradually converted to lithosphere simply by cooling. Oceanic lithosphere continues to thicken until it is about 80 to 100 kilometers thick. Thereafter, its thickness remains relatively unchanged until it is subducted. Spreading rates and ridge topography. When researchers studied various segments of the oceanic ridge system, it became clear that there were topographic differences. These differences appear to have resulted from differences in spreading rates, which largely determine the amount of melt generated at a rift zone. More magma wells up from the mantle at fast-spreading centers than at slow-spreading centers. This difference in output causes differences in the structure and topography of various ridge segments. Oceanic ridges that exhibit slow spreading rates from 1 to 5 centimeters per year have prominent rift valleys and rugged topography. The Mid-Atlantic and Mid-Indian ridges are examples. The vertical displacement of large slabs of oceanic crust along normal faults is responsible for the steep walls of the rift valleys. Furthermore, volcanism produces numerous cones in the rift valley, which enhance the rugged topography of the ridge crest. Figure 10.17 Topography of slow and fast-spreading centers. Figure 10.17 Full alternative text description. By contrast, along the Galapagos Ridge, an intermediate spreading rate of 5 to 9 centimeters per year is the norm. As a result, the rift valleys that develop are relatively shallow, often less than 200 meters deep. In addition, their topography is more subdued compared to ridges that have slower spreading rates. At fast-spreading centers, such as along much of the East Pacific Rise, rift valleys are generally absent. Instead, the ridge axis is elevated. These elevated structures, called swells, are built from lava flows up to 10 meters thick that have incrementally paved the ridge crest with volcanic rocks. In addition, because the depth of the ocean depends largely on the age of the seafloor, ridge segments that exhibit faster spreading rates tend to have more gradual profiles than ridges that have slower spreading rates. Because of these differences in topography, the gently sloping, less rugged portions of fast-spreading ridges are called rises. Figure 10.18 Ridge segments that exhibit fast, intermediate, and slow spreading rates. Figure 10.18 Full alternative text description. Concept checks 10.5. 1. What is the source of magma for seafloor spreading? 2. What is the primary reason for the elevated position of the oceanic ridge system? 3. Why does the lithosphere thicken as it moves away from the ridge as a result of seafloor spreading? 4. Compare and contrast the topography of a slow-spreading center such as the Mid-Atlantic Ridge with one that exhibits a faster spreading rate, such as the East Pacific Rise. 10.6 The nature of oceanic crust. List the 4 layers of oceanic crust and explain how oceanic crust forms and how it differs from continental crust. An interesting aspect of oceanic crust is that its thickness and structure are remarkably consistent throughout the entire ocean basin. Seismic soundings indicate that its thickness averages only about 7 kilometers. Furthermore, it is composed almost entirely of mafic rocks that are underlain by a layer of the ultramafic rock peridotite, which forms the lithospheric mantle. Although most oceanic crust forms out of view, far below sea level, geologists have been able to examine the structure of the ocean floor firsthand. In locations such as Newfoundland, Cyprus, Oman, and California, slivers of oceanic crust and underlying mantle have been thrust high above sea level. From these exposures and core samples collected by deep-sea drilling ships, researchers have concluded that the ocean crust consists of 4 distinct layers. This view of the layered structure of oceanic crust is based on data obtained from ophiolite complexes, seismic profiling, and core samples obtained from deep-sea drilling expeditions. The relative thickness of the layers is not shown to scale. Figure 10.19 Full alternative text description. Layer 1. The upper layer is a sequence of deep-sea sediments or sedimentary rocks. Sediments are very thin near the axes of oceanic ridges but may be several kilometers thick next to continents. Figure 10.19 Structure of the oceanic crust. Layer 2. Below the layer of sediments is a rock unit composed mainly of basaltic lavas that contain abundant pillow-like structures called pillow lavas. Layer 3. The middle, rocky layer is made up of numerous interconnected dikes that have a nearly vertical orientation, called a sheeted dike complex. These dikes are former pathways where magma rose to feed pillow basalts on the ocean floor. Layer 4. The lowest layer is mainly gabbro, the coarse-grained equivalent of basalt, which crystallize deeper in the crust without erupting. When fragments of oceanic crust and the underlying mantle are discovered on land, they are called an ophiolite complex. From studies of various ophiolite complexes around the globe and related data, geologists have pieced together a scenario for the formation of the ocean floor. How does oceanic crust form? The molten rock that forms new oceanic crust originates from partial melting of the ultramafic mantle rock. This process generates basaltic melt that is less dense than the surrounding solid rock. The newly formed melt rises through the upper mantle along thousands of tiny conduits that feed into a few dozen larger, elongated channels, perhaps 100 meters or more wide. These structures, in turn, feed lens-shaped magma chambers located directly beneath the ridge crest. The addition of melt from below steadily increases the pressure inside the magma chambers. As a result, the rocks above these reservoirs periodically fracture, allowing the melt to ascend along numerous vertical fractures that develop in the ocean crust. Some of the melt cools and solidifies to form dikes. New dikes intrude older dikes, which are still warm and weak, to form a sheeted dike complex. This portion of the oceanic crust is usually 1 to 2 kilometers thick. Roughly 10 to 20% of the melt eventually erupts on the ocean floor. Because the surface of these submarine lava flows is chilled quickly by seawater, these flows generally travel no more than a few kilometers before completely solidifying. The forward motion occurs as lava accumulates behind the congealed margin and then breaks through. This process occurs repeatedly, as molten basalt is extruded, like toothpaste from a tightly squeezed tube. The result is protuberances resembling large bed pillows stacked one atop the other, hence the name pillow lavas. This pillow lava is exposed along a sea cliff at Cape Wanbrow, New Zealand. Notice that each pillow shows an outer dark glassy layer created by rapid cooling, which encloses a dark gray basalt interior. Figure 10.20 Cross-sectional view of pillow lava. In some settings, pillow lavas may build volcano-size mounds that resemble shield volcanoes, whereas in other situations they form elongated ridges tens of kilometers long. These structures are eventually separated from their supply of magma as they are carried away from the ridge crest by seafloor spreading. The lowest unit of the ocean crust develops from crystallization within the central magma chamber. The first minerals to crystallize are olivine, pyroxene, and occasionally chromite, which settle through the magma to form a layered zone near the floor of the magma reservoir. The remaining melt tends to cool along the walls of these magma chambers to form massive amounts of coarse-grained gabbro. This portion accounts for up to 5 of the 7 kilometers of ocean crust thickness. Although molten rock rises continuously from the mantle toward the surface, seafloor spreading occurs in pulse-like bursts. As the melt begins to accumulate in the lens-shaped reservoirs, it is blocked from continuing upward by the stiff overlying rocks. As the amount of melt entering the magma reservoirs increases, pressure rises. Periodically, the pressure exceeds the strength of the overlying rocks, which fracture and initiate a short episode of seafloor spreading. Did you know? The circulation of seawater through the oceanic crust extracts heat from the volcanically produced material and is the main method by which the crust is cooled. Interactions between seawater and oceanic crust. In addition to serving as a mechanism for dissipating Earth's internal heat, the interaction between seawater and the newly formed basaltic crust alters both the seawater and the crust. The permeable and highly fractured lava of the upper oceanic crust allows seawater to penetrate to depths of 2 to 3 kilometers. Seawater circulating through the hot crust is heated and chemically reacts with the basaltic rock in a process called hydrothermal metamorphism. This alteration causes the dark silicates in basalt to form new metamorphic minerals such as chlorite and serpentine. Simultaneously, the hot seawater dissolves ions of silica, iron, copper, and occasionally silver and gold from the hot basalts. When the water temperature reaches a few hundred degrees Celsius, these mineral-rich fluids buoyantly rise along fractures and eventually spew out on the ocean floor. Studies conducted by submersibles along several segments of the oceanic ridge have photographed these metallic-rich solutions gushing from the seafloor to form particle-filled clouds called black smokers. As the hot liquid mixes with the cold, mineral-laden seawater, the dissolved minerals precipitate to form massive metallic sulfide deposits, some of which are economically important. Occasionally, these deposits grow upward to form underwater chimney-like structures equivalent in height to skyscrapers. Concept checks 10.6. 1. Briefly describe the four layers of the ocean crust. 2. How does a sheeted dike complex form? 3. How does hydrothermal metamorphism alter the basaltic rocks that make up the seafloor? How is seawater changed during this process? 4. What is a black smoker? 10.7 Continental rifting, the birth of a new ocean basin. Outline the steps by which continental rifting results in the formation of new ocean basins. The breakup of Pangaea nearly 200 million years ago opened a new ocean basin, the Atlantic. Although geoscientists still debate what initiated this event, the breakup of Pangaea illustrates that ocean basins originate when large land masses break apart. Evolution of an ocean basin. The opening of a new ocean basin begins with the formation of a continental rift, an elongated depression along which the entire lithosphere is stretched and thinned. Where the lithosphere is thick, cool, and strong, rifts tend to be narrow, often less than a few hundred kilometers wide. Modern examples of narrow continental rifts include the East African Rift, the Rio Grande Rift, the Baikal Rift, and the Rhine Valley. By contrast, where the crust is thin, hot, and weak, rifts can be more than 1,000 kilometers wide, as exemplified by the Basin and Range region in the western United States. In settings where rifting continues, the rift system evolves into a young, narrow ocean basin, such as the present-day Red Sea. Continued seafloor spreading eventually results in the formation of a mature ocean basin bordered by rift continental margins. The Atlantic Ocean is such a feature. What follows is an overview of ocean basin evolution, using modern examples to represent the various stages of rifting. East African Rift. The East African Rift is a continental rift that extends through eastern Africa for approximately 3,000 kilometers. It consists of several interconnected rift valleys that split into eastern and western sections around Lake Victoria. Whether this rift will eventually develop into a spreading center, with the Somali subplate separating from the rest of the continent of Africa, is uncertain. The map shows the extent of the East African Rift Valley, as well as the Rift Valley that is now occupied by the Red Sea. Smart Figure 10.21 Full alternative text description. Smart Figure 10.21 East African Rift Valley. Watch tutorial, Continental Rifting. The most recent period of rifting began about 20 million years ago, as upwelling in the mantle intruded the base of the lithosphere. Buoyant uplifting of the heated lithosphere led to doming and stretching of the crust. Consequently, the upper crust was broken along high-angle normal faults, producing down-faulted blocks, or grabens, while the lower crust deformed by ductile stretching. Smart Figure 10.22 Formation of an ocean basin. Smart Figure 10.22 Full alternative text description. Watch animation, divergent boundary formation. Did you know? Communities of organisms reside around hydrothermal vents in dark, hot, sulfur-rich environments where photosynthesis cannot occur. The base of the food web is provided by microbes that use a process called chemosynthesis to grow, which allows them and many other organisms to live in this extreme environment. In the early stages of rifting, magma generated by decompression melting of the rising mantle rocks intruded the crust. Occasionally, some of the magma migrated upward along fractures and erupted at the surface. This activity produced extensive basaltic flows within the rift as well as volcanic cones, some forming more than 100 kilometers from the rift axis. Examples include Mount Kenya and Mount Kilimanjaro, the highest point in Africa, which rises almost 6,000 meters above the Serengeti Plain. Red Sea. Gradually, a rift valley lengthens and deepens, until it eventually extends to the margin of the continent. At this point, the continental rift becomes a narrow linear sea with an outlet to the ocean, similar to the Red Sea. The Red Sea formed when the Arabian Peninsula rift from Africa beginning about 30 million years ago. Steep fault scarps that rise as much as 3 kilometers above sea level flank the margins of this water body. Thus, the escarpments surrounding the Red Sea are similar to the steep cliffs that border the East African Rift. Although the Red Sea reaches oceanic depths in only a few locations, symmetrical magnetic stripes indicate that typical seafloor spreading has been occurring for at least the past 5 million years. Atlantic Ocean. If spreading continues, the Red Sea will grow wider and develop an elevated oceanic ridge similar to the Mid-Atlantic Ridge. The Atlantic Ocean shows what the Red Sea could eventually become over tens of millions of years. As the Atlantic formed, new oceanic crust was added to the diverging plates, and the rift continental margins gradually moved away from the region of upwelling. As a result, they cooled, contracted, and sank. Over time, continental margins subsided below sea level, and material that had eroded from the adjacent highlands blanketed this once rugged topography. The result was a passive continental margin on both sides of the Atlantic, consisting of rift continental crust that has been covered by a thick wedge of relatively undisturbed sediment and sedimentary rock. Did you know? Sea turtles, salmon, and other animals travel great distances across the open ocean so that they can lay their eggs in the same location where they were hatched. Recent research suggests that these animals may use Earth's magnetic field for navigation. Interestingly, many animals that have homing abilities also contain minuscule amounts of the magnetic mineral magnetite. Failed rifts. Not all continental rift valleys develop into full-fledged spreading centers. In the central United States, a failed rift extends from Lake Superior into Kansas. This once active rift valley is filled with clastic sedimentary and basaltic rocks that were extruded onto the crust more than 1 billion years ago. Why one rift valley develops into a full-fledged active spreading center while others fail to develop is not fully understood. Location of a failed rift extending from the Great Lakes region to Kansas. Figure 10.23 Failed rift. Figure 10.23 Full alternative text description. Concept checks 10.7. 1. Name a modern example of a continental rift. 2. Briefly describe each of the 4 stages in the formation of an ocean basin. 10.8 Destruction of oceanic lithosphere. Compare and contrast spontaneous subduction and forced subduction. Although new lithosphere is continually being produced at divergent plate boundaries, Earth's surface area is not growing larger. In order to balance the amount of newly created lithosphere, there must be a process whereby oceanic lithosphere is destroyed. Why oceanic lithosphere subducts? The process of plate subduction is complex, and the ultimate fate of oceanic lithosphere is still being debated. Does subducted oceanic crust pile up at the boundary between the upper mantle and the lower mantle, where it is assimilated into the mantle? Or do most plates descend to the core, mantle boundary, where they are heated and eventually rise back toward Earth's surface as mantle plumes? What scientists do know with some certainty is that oceanic lithosphere will resist subduction unless its overall density is greater than that of the underlying asthenosphere. It takes at least 15 million years for a young slab of oceanic lithosphere to cool sufficiently to become denser than the supporting asthenosphere. Spontaneous subduction. Subduction zones can be divided into 2 basic types, based on the nature of the subducting plate. The first type, called a Mariana-type subduction zone, is characterized by old, dense lithosphere sinking into the mantle due to its own weight. The lithosphere entering the Mariana Trench is about 185 million years old, some of the oldest and densest lithosphere in today's oceans. Along this trench, the subducting slab descends into the mantle at a steep angle that approaches 90 degrees. Steep subduction angles produces deep trenches, which account in part for the depth of the Challenger Deep, located at the southern limb of the Mariana Trench. The Mariana and most of the other subduction zones in the western Pacific involve cold, dense lithosphere and therefore exhibit spontaneous subduction. In parts of the Pacific, some oceanic lithosphere exceeds 180 million years in age and descends into the mantle at angles approaching 90 degrees. Young oceanic lithosphere is warm and buoyant, and it tends to subduct at a low angle. Figure 10.24 Full alternative text description. It is important to note that the lithospheric mantle, which makes up about 80% of the descending oceanic slab, drives subduction. Even when the oceanic crust is quite old, its density is still less than that of the underlying asthenosphere. Subduction, therefore, depends on lithospheric mantle that is colder and therefore denser than the underlying asthenosphere. Figure 10.24 The angle of plate subduction depends on the lithosphere's density. When an oceanic slab descends to about 400 kilometers, mineral phase changes enhance subduction. At this depth, the transition of olivine to its compact, much denser spinel structure increases the density of the slab, which helps pull the plate into the subduction zone. Forced subduction. The second type of subduction zone, called the Peru, Chile, type subduction zone, is characterized by younger, hotter, and less dense lithosphere that dips at shallower angles. Along Peru, Chile, type boundaries, the lithosphere is too buoyant to subduct spontaneously, rather, it is forced beneath the overlying plate by compressional forces. In areas where forced subduction occurs, a strong coupling develops between the overlying plate and the subducting plate, which can result in particularly strong and frequent earthquakes. Stated another way, plate motion generates horizontal compressional forces that cause the upper plate and underlying plate to grind against each other. The result can be folding and thickening of the upper plate and sometimes the formation of mountainous terrains such as those we see today in the Andes. Shallow subduction and strong coupling have also been observed in the past decade along the Sunda subduction zone, off the coast of Sumatra, another region that has experienced several major earthquakes. Researchers have also determined that unusually thick units of oceanic crust, those that approach 30 kilometers in thickness, are likely to resist subduction. The Ontong Java Plateau, for example, is a thick oceanic plateau, about the size of Alaska, located in the western Pacific. About 20 million years ago, this plateau reached the trench that forms the boundary between the subducting Pacific plate and the overriding Australian, Indian plate. Apparently too buoyant to subduct, the Ontong Java Plateau clogged the trench. We will consider the fate of crustal fragments that are too buoyant to subduct in the next chapter. Subducting plates, the demise of ocean basins. In the 1970s, geologists began using magnetic stripes and fracture zones on the ocean floor to reconstruct the past 200 million years of plate movement. This research showed that parts of, or even entire, ocean basins have been destroyed along subduction zones. For example, during the breakup of Pangaea shown in Figure 2.22 on page 51, notice that the African plate moved northward, eventually colliding with Eurasia. During this event, the floor of the intervening Tethys Ocean was almost entirely consumed into the mantle, leaving behind a few small remnants, the eastern Mediterranean Sea and the Black Sea. Reconstructions of the breakup of Pangaea also helped investigators understand the demise of the Farallon Plate, a large oceanic plate that once occupied much of the eastern Pacific basin. At the time of the breakup of Pangaea, the Farallon Plate was situated on the eastern side of a spreading center, as shown in Figure 10.25a. The spreading center that generated both the Farallon and Pacific plates is the East Pacific Rise. Because the Farallon Plate was subducting faster than it was being generated, it became steadily smaller. The remaining fragments of the once mighty Farallon Plate are the Juan de Fuca, Cocos, and Nazca plates. Smart Figure 10.25 Full alternative text description. Smart Figure 10.25 The demise of the Farallon Plate. Beginning about 180 million years ago, the Americas were propelled westward as Pangaea broke up and the Atlantic Ocean started to open. As a result, the Farallon Plate began subducting beneath the Americas faster than it was being generated, causing it to decrease in size. The three remaining fragments of the once extensive Farallon Plate include the modern Juan de Fuca, Cocos, and Nazca plates. The westward migration of North America also caused a section of the East Pacific rise to enter the subduction zone that once lay off the coast of California. As this spreading center subducted, it was destroyed and replaced by a transform fault system that currently accommodates the differential motion between the North American and Pacific plates. This change in plate geometry caused the Pacific Plate to capture a sliver of North America that it carries northwestward toward Alaska at an average rate of about 6 centimeters per year. As more of the ridge subducted, the transform fault system, which we now call the San Andreas Fault, increased in length. Today, the southern end of the San Andreas Fault connects to a young spreading center that is generating the Gulf of California. A similar event generated the Queen Charlotte Transform Fault, located off the west coast of Canada and southeastern Alaska. Watch tutorial, the Farallon Plate and the birth of the San Andreas Fault. Concept checks 10.8. Figure 10.26. The separation between the Baja Peninsula and North America. 1. Explain why oceanic lithosphere subducts even though the oceanic crust is less dense than the underlying asthenosphere. 2. Compare spontaneous subduction and forced subduction. Provide examples of places where each operates. 3. What role do mineral phase changes play in plate subduction? 4. Explain what happened when the spreading center that generated the Farallon Plate collided with the North American Plate. Concepts in review: origin and evolution of the ocean floor. 10.1. An emerging picture of the ocean floor. Define bathymetry and describe the various bathymetric techniques used to map the ocean floor. Key terms: bathymetry, sonar, echo sounder. Oceanographers map the seafloor with sonar, shipboard. Instruments that emit pulses of sound that echo off the bottom. Satellites are also used to map the ocean floor. Their instruments measure slight variations in sea level that result from differences in the gravitational pull of features on the seafloor. Mapping efforts have revealed three major areas of the ocean floor: continental margins, deep ocean basins, and oceanic ridges. 10.2. Continental margins. Compare and contrast a passive continental margin with an active continental margin and list the major features of each. Key terms: continental margin, passive continental margin, continental shelf, continental slope, continental rise, turbidity, current, submarine canyon, deep sea fan. Active continental margin, accretionary wedge, subduction, erosion. Continental margins are transitional zones between continental and oceanic crust. Active margins occur along continental plate boundaries where an oceanic slab is subducting beneath a continent. Passive continental margins are on the trailing edge of continents, far from plate boundaries. Heading offshore from the shoreline of a passive margin, a submarine traveler first encounters the gently sloping continental shelf and then the steeper continental slope, which marks the end of the continental crust and the beginning of the oceanic crust. Beyond the continental slope is the continental rise, which is made of sediment transported by turbidity currents. At an active continental margin, material may be added to the leading edge of a continent in the form of an accretionary wedge. Or material may be scraped off the edge of a continent by subduction erosion. What type of continental margin is depicted in this diagram? Name the feature indicated by the question mark. 10.3. Features of deep ocean basins. List and describe the major features of the deep ocean basin. Key terms: deep ocean basin, deep ocean trench, volcanic island arc, continental volcanic arc, abyssal plain. Seismic reflection profiler, seamount, volcanic island, geo-oceanic plateau, atoll. The deep ocean basin makes up about half of the ocean floor's area. Much of it is abyssal plain. Subduction zones and deep ocean trenches also occur in deep ocean basins. Paralleling trenches are volcanic island arcs or continental volcanic arcs. A variety of volcanic structures poke up from the abyssal plain. Seamounts are submarine volcanoes. If they emerge at the ocean's surface, we call them volcanic islands. Guyots are old volcanic islands that have had their tops eroded off before sinking below the sea. Oceanic plateaus are submarine flood basalt provinces, unusually thick sections of oceanic crust formed by massive underwater eruptions of lava. Ring-shaped coral atolls are features formed from biological rather than geological processes around volcanic islands. As these islands erode and sink below the surface, corals build upward on existing coral skeletons to take advantage of sunlight and warm water temperatures. On this cross-sectional view of a deep ocean basin, label the following features: seamount, guyot, volcanic island, oceanic plateau, and abyssal plain. Figure 10.10 to 1 full alternative text description. 10.4 Anatomy of the oceanic ridge. Sketch and label a cross-sectional view of the Mid-Atlantic Ridge. Explain how a cross-section of the East Pacific Rise would look different. Key terms. Oceanic Ridge Rift Valley. The Oceanic Ridge System is the longest topographic feature on Earth, wrapping around the world through all major ocean basins. It is a few kilometers tall, a few thousand kilometers wide, and a few tens of thousands of kilometers long. The ridge summit is where new oceanic crust is generated, and it may be marked by a rift valley. 10.5 Oceanic ridges and seafloor spreading. Write a statement describing how spreading rates affect ridge topography. Oceanic ridges form due to seafloor spreading. As plates of oceanic lithosphere move apart, the warm mantle beneath rises and undergoes decompression melting. The resulting magma is basaltic in composition. Some of it erupts along the ridge axis, but much of it crystallizes at depth. The freshly cooled basalt or gabbro makes up new oceanic crust. Oceanic ridges are elevated features because they are warm and therefore less dense than older, colder oceanic lithosphere that makes up the deep ocean basins. Heat loss causes the oceanic crust to subside and be buried. After 80 million years, crust that was once an oceanic ridge can become an abyssal plain. The rate at which seafloor spreading occurs determines the shape of an oceanic ridge. Ridges with slow spreading rates have prominent rift valleys and rugged topography. Those with fast spreading rates lack rift valleys and show a smoother, more subdued topography. 10.6 The nature of oceanic crust. List the 4 layers of oceanic crust and explain how oceanic crust forms and how it differs from continental crust. Key terms. Ophiolite complex, sheeted dike complex, pillow lava, black smoker. Ophiolite complexes contain slices of oceanic crust that have been thrust above sea level. They have 4 distinct layers: deep sea sediment, pillow lava flows, the sheeted dike complex, and the gabbro layer. As 2 divergent plates move apart, fractures open perpendicular to the stretching direction, and lava moves up through these cracks, toward the seafloor. Once the lava has cooled and sealed these fractures shut, they become preserved as dikes of the sheeted dike complex. Magma that cools at depth crystallizes to become gabbro. Any lava that makes it to the seafloor is erupted as pillow lavas, which are gradually buried by deep-sea sedimentation. Along mid-ocean ridges, seawater flows through fissures in the oceanic crust and is heated by the hot surrounding rock. The warmer the seawater, the more chemically active it becomes. The hot water causes hydrothermal metamorphism and dissolves metal ions. These hot solutions may spew out of the crust as black smokers. 10.7 Continental rifting, the birth of a new ocean basin. Outline the steps by which continental rifting results in the formation of new ocean basins. Key term. Continental rift. When continents rift apart, new ocean basins may form. The East African Rift is an example of the initial stages of continental breakup, with rift valleys that are sites of basaltic volcanism and deposition of detrital sediment. The Red Sea is an ongoing example of more advanced rifting, in which seafloor spreading is occurring and the rift is submerged below sea level. Over time, the rift may widen due to the seafloor spreading, forming an ocean basin flanked by passive continental margins. A modern example of this stage is the Atlantic Ocean. Consider the Baja Peninsula of Mexico. Which stage of continental rifting does the Gulf of California most closely match? 10.8 Destruction of oceanic lithosphere. Compare and contrast spontaneous subduction and forced subduction. Key terms: spontaneous subduction, forced subduction. The production of oceanic lithosphere by seafloor spreading is balanced by subduction, which carries oceanic lithosphere into the mantle. The fate of subducted lithosphere in the mantle is still uncertain. When oceanic lithosphere is sufficiently old, it may begin to sink because of its increased density. The resulting spontaneous subduction zone plunges at an angle near 90 degrees and is marked by a deep trench. The Mariana Trench is an example. Forced subduction shoves relatively buoyant oceanic lithosphere underneath another plate. This results in shallow subduction angles and large earthquakes along megathrust faults. The Peru-Chile Trench is an example. Regardless of its initial cause, subduction serves to close ocean basins. This may eventually bring once widely separated land masses into contact with one another. Which type of subduction is illustrated in this diagram? Describe the age of the oceanic lithosphere at the deep ocean trench compared to that at the oceanic ridge. Figure 10.10 to 1 Full alternative text description. Give it some thought. 1. How many seconds would it take an echo sounder's ping to make the trip from a ship to the Challenger Deep, 10,994 meters, and back? Recall that depth equals 1/2. 2. Referring to figure 10.17, compare and contrast the topography of the crest of an oceanic ridge that exhibits a slow spreading rate with one that exhibits a fast spreading rate. Give examples of each type of ridge. 3. Mataiva is a small atoll in the Tuamotu archipelago, French Polynesia. Using the accompanying map, determine the approximate number of atolls in this small region of the Western Pacific. 4. Refer to the accompanying map, which shows the eastern seaboard of the United States, to complete the following. A. Which letter is associated with each of the following: continental shelf, continental rise, and continental slope? B. How does the size of the continental shelf that surrounds the state of Florida compare with the size of the Florida Peninsula? C. Why are there no deep ocean trenches on this map? Figure 10.10 to 1 Full alternative text description. 5. Briefly explain why the ocean floor generally gets deeper the farther one travels from the ridge crest. 6. The accompanying photo is a false-color sonar image that shows the ridge crest of a section of a spreading center. A. Is the structure along the ridge crest characteristic of a fast-spreading center or a slow-spreading center? Explain. B. What name is given to the submerged cone-shaped structure in the lower left portion of this image? Figure 10.10 to 1 Full alternative text description. 7. Name a location where a new ocean basin may develop in the future. Explain why you chose that site. 8. Refer to figure 10.4. At which of the following locations would you expect to have the highest angle of subduction, the Puerto Rico subduction zone or the Cascadia subduction zone? Explain. 9. Refer to figure 10.25. Predict the fate of the Juan de Fuca plate. What type of boundary might the Cascadia subduction zone become in the future? Explain. 10. Explain this statement. Oceans have existed on Earth for over 4 billion years, but the oldest seafloor that has been dated is only about 200 million years old. 11. This image shows lava at a temperature of about 1200 C erupting on the seafloor west of the Tonga Trench. What name is given to lava flows like these that erupt underwater? Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 11 Crustal Deformation and Mountain Building. Mount Kidd, Alberta, Canada, with Kananaskis River in foreground. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 11.1 Describe the three types of differential stress and identify the tectonic setting most commonly associated with each. Differentiate stress from strain and brittle from ductile deformation. 11.2 List and describe 5 types of folds. 11.3 Sketch and briefly describe the relative motion of rock bodies located on opposite sides of normal, reverse, and thrust faults as well as both types of strike-slip faults. 11.4 Locate and name Earth's major mountain belts on a world map. 11.5 Sketch a cross-section of an Andean-type mountain belt and describe how its major features are generated. 11.6 Summarize the stages in the development of an alpine-type mountain belt such as the Appalachians. 11.7 Explain the principle of isostasy and how it contributes to the elevated topography of mountain belts. Mountains provide some of the most spectacular scenery on our planet. Poets, painters, and songwriters have captured their splendor. Geologists understand that at some time, all continental regions were mountainous masses and that continents grow over time through the addition of mountains to their flanks. Where lithospheric plates collide, the rocks in the collision zone are crumpled and transformed. Even continental interiors hold the remnants of mountain ranges formed from ancient collisions. This chapter explains the forces that create mountains, while the following chapters focus on the processes that weather and carry away rock material to create Earth's varied topography. This chapter was revised with the assistance of Professor Callan Bentley. 11.1 Crustal Deformation. Describe the three types of differential stress and identify the tectonic setting most commonly associated with each. Differentiate stress from strain and brittle from ductile deformation. Young mountain belts tower above the surrounding landscapes, exhibiting steep slopes and high relief. Once the tectonic forces that raised these mountains cease, weathering and erosion will, over long spans of geologic time, grind them down until their roots lie flush with the surrounding topography. Even then their rocks hold clues to their former grandeur and to the forces that created them. Folded and faulted rocks like those in Figure 11.1 attest to the compressional forces that deformed them. Smart Figure 11.1 Deformed sedimentary strata. These deformed strata are exposed in a road cut near Palmdale, California. In addition to the obvious folding, light-colored beds are offset along a fault located on the right side of the photograph. Smart Figure 11.1 Full alternative text description. Watch tutorial, Brittle versus Ductile. What causes rocks to deform? Tectonic forces can cause rocks to move, tilt, and/or change shape. For instance, colliding plates can uplift a flat-lying bed of marine limestone so that it is exposed at the surface, rotate the rock at a steep angle, and crumple it into folds. Collectively, all these types of change are called deformation. Because rock deformation is caused mainly by tectonic forces, it occurs mostly along plate boundaries, the places where lithospheric plates push together, pull apart, or scrape past each other. Rocks deform in characteristic ways that can be observed when the rocks are exposed on Earth's surface as an outcrop. For example, the folds in Figure 11. 1 represent a typical response to compressional forces at depth. Geologists use the term tectonic structures, or geologic structures, for the structural features that we can observe and that reflect a rock's tectonic history. This chapter will look particularly at 3 types of tectonic structures: folds, faults, and joints. To understand rock deformation, we first need to look more closely at the concepts of stress and strain. Stress, the cause of deformation. So far, we've said that tectonic forces cause deformation. More precisely, rocks respond to stress, which takes into account the area over which a force acts. Recall from Chapter 8 that a force applied equally in all directions is called confining pressure, a force that compacts mineral grains to reduce the volume of rock bodies. However, confining pressure does not cause deformation. Instead, most deformation is caused by differential stress, in which the force is stronger in one direction and weaker in another. Figure 11.23 Aspects of differential stress: compression, tension, and shear. Figure 11.2 Full alternative text description. Does stress acting on a rock always deform it? No, obviously not. When you stand on a rock, you press down on it. When you step off, you don't leave a dent. A rock's strength is its resistance to being deformed permanently by a stress. A rock will resist deformation until the stress exceeds its strength. A rock's strength depends on factors such as temperature and confining pressure, as well as the length of time over which the stress is exerted. We will consider three types of differential stress: compressional, tensional, and shear. On a large scale, each type of stress tends to be associated with one type of plate boundary. Compression. Differential stress that squeezes a rock mass as if it is in a vise is known as compressional stress. Compressional stresses are most often associated with convergent plate boundaries. When plates collide, Earth's crust is generally shortened horizontally and thickened vertically. Over millions of years, this deformation produces mountain belts. Tension. Differential stress that pulls apart rock bodies is known as tensional stress. Along divergent plate boundaries, where plates are moving apart, tensional stresses stretch and lengthen rock bodies horizontally and thin them vertically. For example, in the Basin and Range Province in western North America, tensional forces have fractured and stretched the crust to as much as twice its original width. Shear. Differential stress can cause rock to shear, which involves the movement of one part of a rock body past another. An everyday example of shear is the slippage that occurs between individual playing cards when the top of the deck is moved relative to the bottom. Shear is important at transform plate boundaries, such as the San Andreas Fault, where large segments of Earth's crust slip horizontally past one another. Strain, a change in shape caused by stress. Earlier, we said that differential stress can deform a rock body by causing it to move, to tilt, and/or to change shape. When differential stress changes a rock's shape, the resulting deformation is called strain. By observing and measuring the strain imprinted on a rock body, we can infer the type of stress that deformed the rock. How does a rigid object like a rock change its shape? On a microscopic scale, this shape change is often accomplished through shearing. Note that deformation on a large scale often involves shearing on a small scale. There are two main ways in which a solid rock can change its shape by undergoing small-scale shearing. First, a rock can undergo slippage along parallel surfaces of weakness, such as foliation surfaces or microscopic fractures. Like the deck of cards in Figure 11.3, many tiny slips can add up to a significant change in shape. An ordinary deck of playing cards with a circle embossed on its side illustrates shearing and the resulting strain. Figure 11.3 Full alternative text description. Figure 11.3 Shearing and the resulting deformation. Second, shearing can take place within intact mineral grains. This occurs in part because mineral crystals are often far from perfect. The crystal structure may be missing atoms, or the atoms of one element may substitute for those of another. When a crystal undergoes differential stress, these defects are places where bonds can easily break and reform. The result is slippage along microscopic surfaces within the crystal structure, and the mineral grain as a whole gradually changes shape. If mineral crystals were perfect, rocks would be much stronger than they actually are. Mineral grains can also change shape in response to differential stress that does not involve slippage along zones of weakness. This process, called recrystallization, involves the movement of atoms from a location that is highly stressed to a less stressed position on the same grain. Types of deformation. Rocks experience three types of deformation that lead to shape changes: elastic, brittle, and ductile. Elastic deformation. If you have ever opened a door that has a spring attached, you may have noticed that when you let go of the door, the spring pulls the door shut as it returns to its original shape. We say the spring undergoes elastic deformation. It deforms temporarily in response to a stress and returns to its original configuration when the stress is removed. Chemical bonds in a mineral grain act like a spring. When they are elastically deformed, they stretch but do not break, and when the stress is removed, the chemical bonds snap back to their original length. As you saw in Chapter 9, the energy released by most strong earthquakes comes from stored energy that is suddenly released as rock elastically snaps back to its original shape. Brittle deformation. When a rock's strength is exceeded, that is, when it is deformed beyond its ability to respond elastically, it will either break or bend. Rocks that break into smaller pieces exhibit brittle deformation. From our everyday experience, we know that glass objects, wooden pencils, ceramic plates, and even our bones exhibit brittle deformation when their strength is surpassed. Brittle deformation occurs when stress breaks the chemical bonds that hold a material together. Ductile deformation. When an object changes shape without breaking, we say that it has undergone ductile deformation. When you knead clay or taffy, you are deforming it in a ductile way. Ductile deformation in rocks takes place largely through the mechanisms described earlier: slippage along surfaces of weakness within the rock and the gradual reshaping of mineral grains. These processes enable rock to flow very slowly, even though it remains in a solid state. Intricate folds are an example of ductile deformation. Factors that affect how rocks deform. Figure 11.4 compares the types of brittle and ductile deformation. As the figure indicates, rock deformation tends to be brittle at shallow depths and ductile at greater depths. 4 factors influence how a rock deforms: temperature, confining pressure, the type of rock, and time. Brittle deformation dominates in the upper crust, where the temperatures are comparatively cool. By contrast, at depths greater than about 10 kilometers, where temperatures are high, rock deforms by ductile flow and folding. Figure 11.4 deformation caused by 3 types of stress. Figure 11.4 full alternative text description. The role of temperature. Temperature plays a major role in the behavior of rocks. Where temperatures are high, rocks are nearer their melting temperatures and are therefore weaker and more capable of ductile deformation. Near the surface or in a comparatively cool environment such as a subduction zone, rocks are more brittle and prone to fracture. This behavior is completely familiar. A cold chocolate bar snaps between your teeth, whereas a warm one bends in your hand. The role of confining pressure. Recall that the confining pressure on rocks increases with depth as the thickness of the overlying rock increases. Because confining pressure squeezes rocks equally from all directions, it tends to make them harder to break and hence less brittle. Thus, at depth, the increase in temperature and the increase in pressure have complementary effects. The increase in temperature enhances ductile behavior, and the increase in pressure tends to keep the rock intact and thus more likely to bend than to fracture. The influence of rock type. The manner in which a particular rock type responds to stress is greatly influenced by its mineral composition and texture. Granite, basalt, and well-cemented quartz sandstones are examples of strong, brittle rocks that tend to fail by breaking when subjected to stresses that exceed their strength. By contrast, clay-rich or weakly cemented sedimentary rocks and foliated metamorphic rocks more readily exhibit ductile deformation. Weak rocks that are most likely to behave in a ductile manner when subjected to differential stress include rock salt, shale, limestone, and schist. Rock salt consists of intergrown crystals, so you might think that it would resist ductile deformation. In fact, the opposite is true. Salt crystals readily change shape as the mineral grains continually recrystallize in response to differential stresses, which is why salt layers can rise up through other strata to form salt domes. Glacial ice also consists of crystals that deform easily, accommodating internal flow. Some outcrops consist of a sequence of alternating layers of weak and strong rocks that have been deformed. Figure 11.5 shows an example in which adjacent metamorphic rock layers responded very differently to the same differential stress. Notice that the central non-foliated layer broke into chunks, while the flanking foliated layers deformed in a ductile manner, flowing into the gaps between the chunks. The same thing happens when you bite into a s'more, the graham crackers break, while the marshmallow and chocolate layers ooze. This structure is an example of boudinage, which forms when some portions of a rock body deform in a ductile fashion and others act as brittle units. The central greenish layer has been broken into a series of chunks, and the surrounding gray material has flowed into the gaps between the chunks. Figure 11.5 How rock type influences the type of deformation. Did you know? The combination of brittle and ductile behavior seen in the rock in Figure 11.5 resembles links of old-fashioned sausages in a string. Because of this resemblance, the structure is called boudinage, from the French term boudin, meaning sausage. Time as a factor. The folded rocks of mountain belts show that tens of kilometers of compressional strain can be accommodated by ductile deformation. For this to happen, however, stress has to be applied slowly enough that the sluggish processes of ductile deformation can keep up. If stress is applied to a rock unit relatively quickly, the rock will deform elastically until its strength is exceeded, and then it will fracture. Taffy exhibits the same behavior on a more familiar timescale. If you hit a bar of taffy against the edge of a table, it will break, but if you put a weight on it and leave it overnight, it will gradually spread and flatten. In practice, rocks that are near Earth's surface tend to accommodate even gradual strain by fracturing. Ductile behavior happens mainly at depth. Concept checks 11.1. 1. What is deformation? List several ways in which a rock body might change during deformation. 2. List the 3 types of differential stress and briefly describe the changes they can impart to rock bodies. 3. What type of plate boundary is most commonly associated with compressional stress? 4. How is strain different from stress? 5. How is brittle deformation different from ductile deformation? 6. List and describe the 4 factors that affect whether a rock deforms in a brittle or ductile manner. 11.2 Folds, rock structures formed by ductile deformation. List and describe 5 types of folds. Along convergent plate boundaries, rock strata are often bent into a series of wave-like undulations called folds. Folds in flat-lying strata are much like those that would form if you were to hold the ends of a sheet of paper on a flat surface and then push them together. Such folds come in a wide variety of sizes and configurations. Some are broad flexures in which strata hundreds of meters thick have been slightly warped. Others are very tight, even microscopic structures found in metamorphic rocks. Most folds result from compressional stresses that result in a lateral shortening and vertical thickening of the crust. Folds are geologic structures that result when originally planar surfaces, such as sedimentary strata, are permanently bent as a result of deformation. Each layer is bent around an imaginary axis called a hinge line, or simply a hinge. The axial plane divides a fold as symmetrically as possible, while the hinge line traces the points of maximum curvature of any layer. Smart Figure 11.6 Full alternative text description. Smart Figure 11.6 Features associated with symmetrical folds. Watch Condor video, anticlines and synclines. Folds are also described by their axial plane, which is a surface that connects all the hinge lines of the folded strata. In simple folds, the axial plane is vertical and divides the fold into 2 roughly symmetrical limbs. However, the axial plane often leans to one side so that one limb is steeper than the other. Anticlines and synclines. The 2 most common types of folds are anticlines and synclines. Anticlines usually form by the upfolding, or arching, of sedimentary layers. Typically found in association with anticlines are downfolds, or troughs, called synclines. Notice in Figure 11.7 that the limb of an anticline is also a limb of an adjacent syncline. The arched structures, folds that go up in the middle, are anticlines. Their limbs dip away from each another. folds that go down in the middle are synclines. Notice that a limb of an anticline is also the limb of the adjacent syncline. Smart Figure 11.7 Common Types of Folds. Smart Figure 11.7 Full Alternative Text Description. Depending on their orientation, these basic folds are described as symmetrical when the limbs are mirror images of each other and asymmetrical when they are not. The limbs of a symmetrical fold dip in opposite directions but at the same angle. The limbs of an asymmetrical fold dip in opposite directions but at different angles. An asymmetrical fold is said to be overturned if both limbs dip in the same direction, with one limb tilted beyond the vertical. An overturned fold can also lie on its side so that the axial plane is horizontal. These recumbent folds are common in highly deformed mountain belts such as the Alps. Watch tutorial, Folds. Folds can also be tilted by tectonic forces so their hinge lines slope downward. Folds of this type are said to plunge because the hinge lines penetrate Earth's surface. Sheep Mountain, Wyoming, is an example of a plunging anticline. Notice in Figure 11.8b that a V-shaped pattern is produced when erosion removes the upper layers of a plunging fold and exposes its interior. In the case of an anticline, such as Sheep Mountain, the tip of the V points in the direction of plunge. The opposite is true for a syncline. Eroded plunging anticlines, like Sheep Mountain, have an outcrop pattern that points in the direction of plunge. Smart Figure 11.8 Full Alternative Text Description. Smart Figure 11.8 Sheep Mountain, Wyoming. A good example of the topography that can result when erosional forces attack folded sedimentary strata is found in the Valley and Ridge province of the Appalachians. It is important to realize that anticlines typically do not show up as ridges, nor do synclines show up as valleys. Rather, ridges and valleys result from differential weathering and erosion. For example, in the Valley and Ridge province, resistant sandstone beds remain as imposing ridges separated by valleys that are cut into more easily eroded shale or limestone beds. Domes and basins. When a broad upwarping of basement rock deforms the overlying cover of sedimentary strata to produce a circular or slightly elongated bulge, the feature is called a dome. The Black Hills of western South Dakota represent a large structural dome generated by upwarping. Here erosion has stripped away the highest portions of the overlying sedimentary beds, exposing older igneous and metamorphic rocks in the center. Watch Mobile Field Trip, Sheep Mountain. Gentle upwarping and downwarping of crustal rocks produce domes and basins. Erosion of these structures results in an outcrop pattern that is roughly circular or a more elongated ellipse. Smart Figure 11.9 Full Alternative Text Description. The central core of the Black Hills is composed of resistant Precambrian age igneous and metamorphic rocks. The surrounding rocks are mainly younger limestones and sandstones. Smart Figure 11.9 Domes versus Basins. Watch tutorial, Domes and Basins. Figure 11.10 The Black Hills of South Dakota, a large structural dome. Figure 11.10 Full Alternative Text Description. Structural domes can also be formed by the intrusion of magma, as shown in Figure 4.26. In addition, the upward migration of buried salt deposits can produce salt domes like those beneath the Gulf of Mexico. Salt domes are economically important rock structures because when salt migrates upward, the surrounding oil-bearing sedimentary strata deform to form oil reservoirs. The inverse of a dome is a downwarped structure termed a basin. Several large structural basins exist in the United States. The basins of Michigan and Illinois have gently sloping beds similar to saucers. These basins are thought to have resulted from large accumulations of sediment, whose weight caused the crust to subside. A few structural basins may have resulted from giant meteorite impacts. The youngest rocks are centrally located, and the oldest beds flank this structure. Figure 11.11 Full Alternative Text Description. Figure 11.11 The bedrock geology of the Michigan Basin. Because structural basins usually contain sedimentary beds sloping at low angles, they are identified by the age of the rocks composing them. The youngest rocks are found near the center, and the oldest rocks are at the flanks. By contrast, in a dome, such as the Black Hills, the oldest rocks form the core. Monoclines. Although we have separated our discussion of folds and faults, they often actually occur together as a result of the same tectonic stresses. One example can be found in broad, regional features called monoclines. Particularly prominent features of the Colorado Plateau, monoclines, mono. Equals 1, clinon equals incline, are large, step-like folds in otherwise horizontal sedimentary strata. These folds appear to have resulted from the reactivation of ancient, steep-dipping reverse faults located in basement rocks beneath the plateau. As large blocks of basement rock were displaced upward, the comparatively ductile sedimentary strata above responded by draping over the fault like clothes hanging over a bench. Displacement along these reactivated faults can exceed 1 kilometer. Smart Figure 11.12 The East Kaibab Monocline, Arizona. This monocline consists of bent sedimentary beds that were deformed by faulting in the bedrock below. The thrust fault does not reach the surface. Other examples of monoclines found on the Colorado Plateau include the Water Pocket Fold and the San Rafael Swell. The inclined strata once extended over the sedimentary layers now exposed at the surface, evidence that a tremendous volume of rock has been eroded from this area. Smart Figure 11.12 Full alternative text description. Watch Condor video, Monoclines of the Colorado Plateau. Concept checks 11.2. 1. Distinguish between anticlines and synclines, between domes and basins, and between anticlines and domes. 2. Draw a cross-sectional view of a symmetrical anticline. Include a line to represent the axial plane and label both limbs. 3. The Black Hills of South Dakota is a good example of what type of geologic structure. 4. Where are the youngest rocks in a structural basin found, near the center or near the margin? 5. Describe how a monocline forms. By strict definition, an anticline is a structure in which the oldest strata are found in the center, and a syncline is a structure where the youngest strata are found in the center. 11.3 Faults and joints, rock structures. Formed by brittle deformation. Sketch and briefly describe the relative motion of rock bodies located on opposite sides of normal, reverse, and thrust faults as well as both types of strike-slip faults. Faults and joints are both structures that form where brittle deformation leads to fracturing of Earth's crust. A joint is simply a fracture, whereas a fault is a fracture along which motion has occurred, so that the rocks on either side are offset from each other. Figure 11.13 shows a small fault revealed in a road cut, where the sedimentary beds have been offset by a few meters. Faults of this scale usually occur as single discrete breaks. By contrast, large faults, like the San Andreas Fault in California, have displacements of hundreds of kilometers and consist of many interconnecting fault surfaces. These structures, described as fault zones, can be several kilometers wide and are often easier to identify from aerial photographs than at ground level. Sudden movements along faults cause most earthquakes. However, the vast majority of faults are remnants of past deformation and are inactive. Smart Figure 11.13 Faults are fractures where slip has occurred. Watch Condor video, Faults versus joints. Dip-slip faults. Faults in which movement is primarily parallel to the slope of the fault surface are called dip-slip faults. Geologists identify the rock surface immediately above the fault as the hanging wall block and the rock surface below as the footwall block, Figure 11. 14. These names were first used by prospectors and miners who excavated metallic ore deposits such as gold that had precipitated from hydrothermal solutions along inactive fault zones. The miners would walk on the rocks below the mineralized fault zone and hang their lanterns on the rocks above. The rock immediately above a fault surface is the hanging wall block, and the one below is called the footwall block. These terms were coined by miners who excavated ore deposits that formed along fault zones. The miners hung their lanterns on the rocks above the fault trace and walked on the rocks below the fault trace. Smart Figure 11.14 Hanging Wall Block and Footwall Block. Smart Figure 11.14 Full Alternative Text Description. Vertical displacements along dip-slip faults tend to produce long, low cliffs called fault scarps. Fault scarps, such as the one shown in Figure 11.15, are produced by rapid vertical slips that generate earthquakes. This fault scarp was created during the Alaska earthquake of 1964. Watch animation, faults. Figure 11.15 Fault scarp. There are two kinds of dip-slip faults, normal faults and reverse faults. Normal faults. When the hanging wall block moves down relative to the footwall block, dip-slip faults are classified as normal faults. Normal faults are associated with tensional stresses that pull rock units apart, thereby lengthening the crust laterally and thinning it vertically. This pulling apart can be accomplished either by uplift that causes the surface to stretch and break or by horizontal forces that have opposing orientations. These faults are called normal faults because it is normal for gravity to pull a block of rock down an inclined plane. Smart Figure 11.16 Normal Dip-Slip Fault. The upper diagram illustrates the relative displacement that occurs between the blocks on either side of a fault. The lower diagram shows how erosion may alter the upfaulted blocks. Smart Figure 11.16 Full Alternative Text Description. Watch tutorial, faults. Normal faults occur in a variety of sizes. Some are small, having displacements of only a meter or so, like the one shown in the road cut in Figure 11.13. Others, however, extend for tens of kilometers. Most large normal faults have relatively steep dips at the surface but tend to flatten out with depth. In the western United States, large normal faults are associated with structures called fault block mountains. Excellent examples of fault block mountains are found in the Basin and Range Province, a region that encompasses Nevada and portions of the surrounding states. Here the crust has been elongated and broken to create more than 200 relatively small mountain ranges. Averaging about 80 kilometers in length, the ranges rise 900 to 1,500 meters above the adjacent downfaulted topographic basins. Here, tensional stresses have elongated and fractured the crust into numerous blocks. Movement along these faults has tilted the blocks, producing parallel mountain ranges called fault block mountains. The downfaulted blocks form basins, whereas the upfaulted blocks erode to form rugged mountainous topography. In addition, numerous tilted blocks form both basins and mountains. Smart Figure 11.17 Normal faulting in the Basin and Range Province. Smart Figure 11.17 Full Alternative Text Description. The topography of the Basin and Range Province evolved in association with a system of normal faults trending roughly north-south. Movements along these faults produced alternating uplifted fault blocks called horsts and downdropped blocks called grabens. Horsts form the ranges and are the source of sediments that have accumulated in the topographic basins created by the grabens. As Figure 11.17 illustrates, structures called half-grabens, which are tilted fault blocks, also contribute to the alternating topographic highs and lows in the Basin and Range Province. Watch Mobile Field Trip, Death Valley. Did you know? Many faults do not reach the surface and hence do not produce a fault scarp during an earthquake. Faults of this type are termed blind, or hidden faults. The 1994 Northridge earthquake in California occurred along a blind thrust fault, as did the 2011 Mineral, Virginia, earthquake. Also notice in Figure 11.17 that the slopes of many of the large normal faults in the Basin and Range Province decrease with depth and eventually join to form a low-angle, nearly horizontal fault called a detachment fault. These faults represent a major boundary between the rocks below, which exhibit ductile deformation, and the rocks above, which exhibit mainly brittle deformation. Reverse and thrust faults. Dip-slip faults in which the hanging wall block moves up relative to the footwall block are called reverse faults. A thrust fault is a type of reverse fault in which the dip is less than 45 degrees. Reverse and thrust faults result from compressional stresses that produce horizontal shortening of the crust. Reverse faults are generated by compressional stresses that force one block of rock over another. Smart Figure 11.18 Full alternative text description. Smart Figure 11.18 Reverse faults. Watch animation, reverse faults. Most high-angle reverse faults are small and accommodate local displacements in regions dominated by other types of faulting. Thrust faults, on the other hand, exist at all scales, with some large thrust faults having displacements ranging from tens to hundreds of kilometers. Movement along a thrust fault can cause the hanging wall block to be thrust nearly horizontally over the footwall block, as shown in Figure 11.19. Thrust faults are a type of reverse fault having dips less than 45 degrees. Smart Figure 11.19 Full alternative text description. Smart Figure 11.19 Thrust fault. Watch animation, thrust faults. Thrust faulting is most pronounced along convergent plate boundaries. Compressional forces associated with colliding plates generally create folds as well as thrust faults that thicken and shorten the crust to produce mountainous topography. Examples of mountainous belts produced by this type of compressional tectonics include the Alps, Northern Rockies, Himalayas, and Appalachians. Strike-slip faults. A fault in which the dominant displacement is horizontal and parallel to the trend of the fault surface is called a strike-slip fault. The earliest scientific records of strike-slip faulting were made following surface ruptures that produced large earthquakes. One of the most noteworthy of these was the Great San Francisco earthquake of 1906. During this strong earthquake, structures such as fences and roads that were built across the San Andreas Fault were displaced as much as 4.7 meters. Because movement along the San Andreas Fault causes the crustal block on the opposite side of the fault to move to the right as you face the fault, it is called a right lateral strike-slip fault. The block diagram illustrates the features associated with large strike-slip faults. Notice how the stream channels have been offset by fault movement. Aerial view of the San Andreas Fault. Figure 11.20 Strike-slip faults. Figure 11.20 Full alternative text description. The Great Glen Fault in Scotland, which exhibits displacement in the opposite direction, is a well-known example of a left lateral strike-slip fault. Associated with the crushed-up rock along the Great Glen Fault trace are numerous lakes, including the legendary Loch Ness. As discussed in Chapter 2, transform faults are a unique class of strike-slip faults that slice through Earth's lithosphere and accommodate motion between two tectonic plates. Most transform faults cut the oceanic lithosphere and link spreading oceanic ridges. Others accommodate displacement between continental blocks that slip horizontally past each other. Some of the best-known transform faults include California's San Andreas Fault, New Zealand's Alpine Fault, the Middle East's Dead Sea Fault, and Turkey's North Anatolian Fault. Large transform faults like these accommodate relative displacements of up to several hundred kilometers. Rather than being a single fracture, most continental transform faults consist of a zone of roughly parallel fractures. While this zone may be up to several kilometers wide, the most recent movement is often along a strand only a few meters wide, which may offset features such as stream channels. Crushed and broken rocks produced during faulting are more easily eroded, so depressions such as linear valleys often mark the locations of large strike-slip faults. Did you know? The lake that is the home of the legendary Loch Ness Monster is located along the Great Glen Fault that divides northern Scotland. Strike-slip movement along this fault zone shattered a wide zone of rock, which glacial erosion subsequently removed, to produce the elongated valley in which Loch Ness is situated. Broken rock is easily eroded, a fact that accounts for the great depth of Loch Ness, as much as 600 feet below sea level. Joints. Among the most common rock structures are fractures called joints. As mentioned earlier, joints differ from faults because no appreciable displacement has occurred along the fracture. Although some joints have a random orientation, most occur in roughly parallel groups. We have already considered two types of joints. Recall from Chapter 4 that columnar joints form when igneous rocks cool and develop shrinkage fractures that produce elongated, pillar-like columns. In addition, recall from Chapter 6 that sheeting produces a pattern of gently curved joints that develop more or less parallel to the surface of large exposed igneous bodies such as batholiths. Here the jointing results from the gradual expansion that occurs when erosion removes the overlying load and reduces pressure on the rock. Most joints are produced when rocks in the outermost crust are deformed, causing the rock to fail by brittle fracture. Extensive joint patterns often develop in response to relatively subtle and often barely perceptible regional upwarping and downwarping of the crust. Many rocks are broken by 2 or even 3 sets of intersecting joints that slice the rock into numerous regularly shaped blocks. These joint sets often exert a strong influence on other geologic processes. For example, chemical weathering tends to be concentrated along joints, and joint patterns influence how groundwater moves through the crust. Because jointing weakens rocks, highly jointed rocks present a risk to construction projects, including bridges, highways, and dams. Figure 11.21 Joint control of landforms. This sea arch in northern Scotland displays a stair-step weathering pattern because it breaks more or less equally along planes of bedding and 2 sets of parallel joints. One of the joint sets is vertical and forms the side of the arch facing the camera, the other is perpendicular to that, highlighted with the red lines. As a result, chemical weathering tends to be concentrated along joints. This image shows the joint pattern called tessellated pavement, located at Eaglehawk Neck, Tasmania, Australia. Figure 11.22 Joint patterns influence how groundwater moves through the crust. On June 5, 1976, the Teton Dam in Idaho failed, taking 14 lives and causing nearly $1 billion in property damage. This earthen dam, constructed of easily eroded clays and silts, was situated on highly fractured volcanic rocks. Although attempts were made to fill the voids in the jointed rock, water gradually penetrated the subsurface fractures and undermined the dam's foundation. Eventually the moving water cut a tunnel into the easily erodible clays and silts. Within minutes the dam failed, sending a 20-meter high wall of water down the Teton and Snake rivers. Jointed rocks can be beneficial to humans. Some of the world's largest and most important mineral deposits are located along joint systems. Hydrothermal solutions can migrate into fractured host rocks and precipitate economically significant amounts of copper, silver, gold, zinc, lead, and uranium. Concept checks 11.3. 1. Contrast the movements that occur along normal and reverse faults. What type of stress is responsible for each kind of fault? 2. What type of fault is associated with fault block mountains? 3. How are reverse faults different from thrust faults? In what way are they similar? 4. Describe the relative movement along a strike-slip fault. 5. How are joints different from faults? 11.4 Mountain building. Locate and name Earth's major mountain belts on a world map. Mountain building has occurred in the recent geologic past at several locations around the world. Young mountain belts include the American Cordillera, which runs along the western margin of the Americas from southernmost South America to Alaska and includes both the Rockies and the Andes, the Alpine, Himalaya chain, which extends along the margin of the Mediterranean, through Iran to northern India and into Indochina, and the mountainous terrains of the western Pacific, which include volcanic island arcs like Japan, the Philippines, and much of Indonesia. Most of these young mountain belts have formed in the past 100 million years. Some, including the Himalayas, began their growth as recently as 50 million years ago. Figure 11.23 Earth's major mountain belts. Notice the east-west trend of major mountain belts in Eurasia in contrast to the north-south trend of the North and South American Cordilleras. Figure 11.23 Full alternative text description. In addition to these young mountain belts, there are several chains of Paleozoic age mountains on Earth. Although these older mountain belts are deeply eroded and topographically less prominent, they exhibit the same structural features found in younger mountains. The Appalachians in the eastern United States and the Urals in Russia are classic examples of this group of older, well-worn mountain belts. The term for the processes that collectively produce a mountain belt is orogenesis. An episode of mountain building is called an orogeny. Most major mountain belts display striking visual evidence of great compressional forces that have shortened the crust horizontally while thickening it vertically. These collisional mountains usually result from the collision of one or more small crustal fragments to a continental margin or from the closure of an ocean basin that results in the collision of two major land masses. As a consequence, collisional mountains contain large quantities of pre-existing sediments and sedimentary rocks that at one time lay along the margin of a continent and were subsequently faulted and contorted into a series of folds. Although folding and thrust faulting are often the most conspicuous signs of orogenesis, varying degrees of metamorphism and igneous activity are always present. Did you know? During Charles Darwin's famous voyage on the HMS Beagle, he experienced a strong earthquake that accompanied sudden uplift of the land around the Bay of Concepcion in Chile. From this and other observations, Darwin concluded that the uplift he witnessed marked one step in the elevation of a mountain chain. The theory of plate tectonics provides a model for orogenesis with excellent explanatory power. It accounts for the origin of virtually all the present mountain belts and most of the ancient ones. According to this model, the tectonic processes that generate Earth's major mountainous terrains occur along convergent plate boundaries. We will next revisit the nature of convergent plate boundaries and then examine how the process of subduction has driven mountain building around the globe. Concept checks 11.4. 1. Define orogenesis. 2. Which type of plate boundary is most directly associated with Earth's major mountain belts? 11.5 Subduction and mountain building. Sketch a cross-section of an Andean-type mountain belt and describe how its major features are generated. Where oceanic lithosphere subducts beneath oceanic lithosphere, a volcanic island arc and related tectonic features develop. Subduction of oceanic beneath continental lithosphere, on the other hand, results in the formation of a continental volcanic arc and mountainous topography along the margin of a continent. Acting like a conveyor belt, oceanic lithosphere may also bring volcanic island arcs and other crustal fragments to a subduction zone. These crustal elements are generally too buoyant to subduct, so they become welded to the overriding plate, which may be another small crustal fragment or a continent. If subduction continues long enough, it can ultimately lead to the closure of an ocean basin and the ensuing collision of two continents. Island arc, type mountain building. Island arcs result from the steady subduction of oceanic lithosphere under oceanic lithosphere, which may continue for 200 million years or more. Periodic volcanic activity, the emplacement of igneous plutons at depth, and the accumulation of sediment that is scraped from the subducting plate gradually increase the volume of crustal material capping the upper plate. Some large volcanic island arcs, such as Japan, owe their size to having been built on fragments of continental crust that have rifted from a large landmass or to the joining of multiple island arcs over time. A volcanic island arc forms where one slab of oceanic lithosphere is subducted beneath another slab of the same material. Figure 11.24 Full alternative text description. Figure 11.24 Development of a volcanic island arc. The continued growth of a volcanic island arc can generate mountainous topography consisting of nearly parallel belts of igneous and metamorphic rocks. This activity, however, is viewed as just one phase in the development of Earth's major mountain belts. As you will see later, some volcanic arcs are carried by subducting plates to the margin of large continental blocks, where they become involved in large-scale mountain building episodes. Andean-type mountain building. Andean-type mountain building is characterized by subduction beneath a continent rather than oceanic lithosphere, as in the Andes Mountains of South America. Subduction along these active continental margins is associated with long-lasting magmatic activity that builds continental volcanic arcs. The result is crustal thickening, with the crust reaching thicknesses of more than 70 kilometers. The first stage in the development of Andean-type mountain belts occurs along passive continental margins. The east coast of the United States provides a modern example of a passive continental margin where sedimentation has produced a thick platform of shallow-water sandstones, limestones, and shales. At some point, the forces that drive plate motions change, and a subduction zone develops along the margin of the continent. This subduction zone may form because the oceanic lithosphere here is so old and dense that it begins to sink of its own accord. Alternatively, strong compressional forces may help to initiate subduction. Figure 11.25 Full alternative text description. Figure 11.25 Andean-type mountain building. Did you know? The highest city in the world, La Paz, Bolivia, is located 3,640 m above sea level, more than twice as high as Denver, Colorado. Bolivia is still rising. Estimates for uplift rates in the central Andes over the past 5 million years range between 0.2 and 3 mm per year. Building volcanic arcs. Recall that as oceanic lithosphere descends into the mantle, increasing temperatures and pressures drive volatiles from the crustal rocks. These mobile fluids migrate upward into the wedge-shaped region of mantle between the subducting slab and upper plate. At a depth of about 100 kilometers, these fluids reduce the melting point of hot mantle rock sufficiently to trigger partial melting. Partial melting of the ultramafic mantle rock peridotite generates magmas with basaltic compositions. Because these newly formed basaltic magmas are less dense than the rocks from which they originated, they will buoyantly rise. In continental settings, basaltic magma often ponds beneath the less dense rocks of the crust. The hot basaltic magma may heat these overlying crustal rocks sufficiently to generate a silica-rich magma of intermediate and/or felsic composition that can rise to form the continental volcanic arc characteristic of an Andean-type subduction zone. Emplacement of batholiths. Because of its low density and great thickness, continental crust significantly impedes the ascent of molten rock. Consequently, much of the magma that intrudes Earth's crust never reaches the surface. Instead, it crystallizes at depth to form massive collections of igneous plutons called batholiths. The result of this activity is thickening of Earth's crust. Eventually, uplift and erosion exhume the batholiths. The American Cordillera contains several large batholiths, including the Sierra Nevada batholith of California, the Coast Range batholith of western Canada, and several large igneous bodies in the Andes. Most batholiths consist of intrusive igneous rocks that range in composition from granite to diorite. Development of an accretionary wedge. During the development of volcanic arcs, unconsolidated sediments that are carried on the subducting plate, as well as fragments of oceanic crust, may be scraped off and plastered against the edge of the overriding plate, like a wedge of soil scraped up by an advancing bulldozer. The resulting chaotic accumulation of deformed and thrust-faulted sediments and scraps of ocean crust is called an accretionary wedge. Some of the sediments in an accretionary wedge are muds that accumulated on the ocean floor and were carried to the subduction zone by plate motion. Additional materials are derived from an adjacent continental volcanic arc and consist of volcanic debris and products of weathering and erosion. Where sediment is plentiful, prolonged subduction may thicken a developing accretionary wedge so that it protrudes above sea level. This has occurred along the southern end of the Puerto Rico Trench, where the Orinoco River basin of Venezuela is a major source of sediments. The resulting wedge emerges to form the island of Barbados. Forearc basins. As an accretionary wedge thickens, it acts as a barrier to the movement of sediment from the volcanic arc to the trench. As a result, sediments begin to collect between the accretionary wedge and the volcanic arc. This region, which is composed of relatively undeformed layers of sediment and sedimentary rocks, is called a forearc basin. Subsidence and continued sedimentation in forearc basins can generate a sequence of nearly horizontal sedimentary strata that can attain thicknesses of several kilometers. Sierra Nevada, Coast Ranges, and Great Valley. California's Sierra Nevada, Coast Ranges, and Great Valley are excellent examples of the tectonic structures that are typically generated along an Andean-type subduction zone. These structures were produced by the subduction of a portion of the Pacific Basin under the western margin of California. The Sierra Nevada batholith is a remnant of the continental volcanic arc that was produced by many intrusions of magma over a span of more than 100 million years. The coast ranges were built from the vast accumulation of sediments that collected along the continental margin. Beginning about 30 million years ago, subduction gradually ceased along much of the margin of North America, as the spreading center that produced the Farallon Plate entered the California Trench. The uplifting and erosion that followed removed most of the evidence of past volcanic activity and exposed the core of crystalline igneous and associated metamorphic rocks that make up the Sierra Nevada. The coast ranges were uplifted only recently, as evidenced by the young, unconsolidated sediments that currently blanket portions of these highlands. California's Great Valley is a remnant of the Forark Basin that formed between the Sierra Nevada and the accretionary wedge and trench that lay offshore. Throughout much of its history, portions of the Great Valley lay below sea level. This sediment-laden basin contains thick marine deposits and debris eroded from the adjacent continental volcanic arc. Concept checks 11.5. 1. Compare and contrast mountain building at a volcanic island arc with mountain building at an Andean-style continental margin. 2. Describe and give an example of a passive continental margin. 3. In what ways are the Sierra Nevada and the Andes similar? 4. What is an accretionary wedge? Briefly describe its formation. 5. What is a batholith? In what tectonic setting are batholiths being generated? 11.6 Collisional mountain belts. Summarize the stages in the development of an alpine-type mountain belt such as the Appalachians. Most major mountain belts are generated when one or more buoyant crustal fragments collide with a continental margin as a result of subduction. Whereas oceanic lithosphere, which is relatively dense, readily subducts, continental lithosphere contains significant amounts of low-density crustal rocks and is therefore too buoyant to be subducted deeply or permanently. Consequently, the arrival of a crustal fragment at a trench results in a collision between the two continental blocks. Cordilleran-type mountain building. A Cordilleran-type orogeny, named after the North American Cordillera, is associated with the Pacific-like ocean, in that, unlike the Atlantic, the Pacific may never close. The rapid rate of seafloor spreading in the Pacific Basin is balanced by a high rate of subduction. In this setting, island arcs and small crustal fragments are often carried along until they collide with an active continental margin and accrete onto it. This process of collision and accretion has generated many of the mountainous regions that rim the Pacific. These accreted blocks of crust are called terranes. Geologists use this term to describe any crustal fragment that consists of a distinct and recognizable series of rock formations and has been transported and accreted by plate tectonic processes. Notice that terrane is a different word from terrain. The two are pronounced the same, but terrain refers to the shape of the surface topography or lay of the land. The nature of terranes. What is the nature of the crustal fragments that have become terranes? Some may have been microcontinents similar to the modern-day island of Madagascar, located east of Africa in the Indian Ocean. Many others were island arcs similar to Japan, the Philippines, and the Aleutian Islands. Still others may have been submerged oceanic plateaus created by massive submarine outpourings of basaltic lavas. More than 100 of these relatively small crustal fragments exist in the modern world. Figure 11.26 Distribution of present-day oceanic plateaus and other submerged crustal fragments. These blocks of crust, shaded orange, could someday be accreted to continents as new terranes. Figure 11.26 Full alternative text description. Accretion and orogenesis. Small structures such as seamounts are generally subducted along with the descending oceanic slab. However, thick sections of oceanic crust, such as the Ontong Java Plateau or an island arc dominated by low-density andesitic igneous rocks, are too buoyant to subduct. In these situations, a collision between the crustal fragment and the continental margin occurs. The sequence of events that happen when small crustal fragments reach a Cordilleran-type margin is shown in Figure 11.27. The upper crustal layers are peeled from the descending plate and thrust in relatively thin sheets onto the adjacent continental block. Convergence does not generally end with the accretion of a crustal fragment. Rather, new subduction zones typically form seaward of the accreted terrain, and they can carry other island arcs or microcontinents toward a collision with the continental margin. Each collision displaces earlier accreted terrains further inland, adding to the zone of deformation as well as to the thickness and lateral extent of the continental margin. Smart Figure 11.27 Collision and accretion of small crustal fragments to a continental margin. Smart Figure 11.27 Full alternative text description. Watch tutorial, Terrain accretion. The North American Cordillera. The correlation between mountain building and the accretion of crustal fragments was first developed in studies of the North American Cordillera. Researchers determined that some of the rocks in the orogenic belts of Alaska and British Columbia contained fossil and paleomagnetic evidence indicating that these strata previously lay much closer to the equator. Paleomagnetic studies and fossil evidence indicate that some of these terrains originated thousands of kilometers to the south and west of their present locations. Smart Figure 11.28 Terrains that have been added to western North America during the past 200 million years. Smart Figure 11.28 Full alternative text description. Watch animation, Terrain formation. It is now known that many of the terrains that make up the North American Cordillera were scattered throughout the Pacific, like the island arcs and oceanic plateaus currently distributed in the western Pacific. During the breakup of Pangaea, the eastern portion of the Pacific Basin began to subduct under the western margin of North America. This activity resulted in many additions of crustal fragments along the entire Pacific margin of the continent, from Mexico's Baja Peninsula to northern Alaska. Geologists expect that many modern microcontinents will likewise be accreted to active continental margins surrounding the Pacific, producing new orogenic belts. Alpine-type mountain building, continental collisions. Alpine-type orogenies are episodes of mountain building that occur where two continental masses collide. They are named after the Alps, which have been intensively studied for more than 200 years. Mountain belts formed by the closure of major ocean basins include the Himalayas, Appalachians, Urals, and Alps. Continental collisions result in the development of mountains characterized by laterally shortened and vertically thickened crust, achieved through deformation such as folding and large-scale thrust faulting. Prior to the collision of the two large land masses, this type of orogeny may also involve the accretion of smaller continental fragments or island arcs that occupied the ocean basin that once separated the two continental blocks. The zone where two continents collide and are welded together is a suture. The same term can be used to describe the boundary between two adjacent accreted terrains. This portion of a mountain belt often preserves slivers of oceanic lithosphere that were trapped between the colliding plates. The unique structure of these pieces of oceanic lithosphere, called ophiolites, help identify the collision boundary. Did you know? During the assembly of Pangaea, the land masses of Europe and Siberia collided to produce the Ural Mountains. Long before the discovery of plate tectonics, this extensively eroded mountain chain was regarded as the boundary between Europe and Asia. Next, we will take a closer look at two examples of collisional mountains, the Himalayas and the Appalachians. The Himalayas, Earth's youngest collisional mountains, are still rising. By contrast, the Appalachians are a much older mountain belt, in which active mountain building ceased about 250 million years ago. The Himalayas. The mountain building episode that created the Himalayas began between 50 and 30 million years ago, when India began to collide with Asia. Prior to the breakup of Pangaea, India was located between Africa and Antarctica in the southern hemisphere. As Pangaea fragmented, India moved rapidly, geologically speaking, a few thousand kilometers in a northward direction. The subduction zone that facilitated India's northward migration was near the southern margin of Asia. continued subduction along Asia's margin created an Andean-type plate margin that contained a well-developed continental volcanic arc and an accretionary wedge. India's northern margin, on the other hand, was a passive continental margin consisting of a thick platform of shallow water sediments and sedimentary rocks. These diagrams illustrate the collision of India with the Eurasian plate that produced the spectacular Himalayas. Smart Figure 11.29 Continental collision, the formation of the Himalayas. Smart Figure 11.29 Full alternative text description. Geologists have determined that 2 or perhaps more small crustal fragments were positioned on the subducting plate somewhere between India and Asia.